Welcome to the concluding lecture on fuel cells. Here we would revisit some of the concepts which we have already introduced in the context of fuel cell. Specifically, in an earlier lecture, we had elaborated the way to rationalize the polarization curve of a fuel cell. That is, when you plot the potential that you can obtain from a fuel cell, it is a function of the current that is drawn from a fuel cell. And we had elaborated the meaning of activation overpotential, ohmic overpotential, and the overpotential due to mass transfer limitation. All these things have to be taken into account to rationalize the potential which you can get from a fuel cell. And we had also contrasted the behavior of a PEM fuel cell against the solid oxide fuel cell in terms of the different overpotential that exist in a fuel cell that operates at a low temperature and in a fuel cell that operates at a high temperature. So please revisit this lecture to make sure you understand these overpotentials in the context of fuel cell. Practically, there are three geometries for a solid oxide fuel cell. It is either anode supported, electrolyte supported, or cathode supported. What do you mean by that? In order to provide mechanical support or to retain the mechanical integrity of a fuel cell, one of the three component has a greater volume. Here it is the anode, which essentially supports the other two components. Here it's the electrolyte. Here it is the cathode. These three geometries have different advantages. We are not going to elaborate these issues, but you should be aware that SOFCs come in these three geometries. But the essential determinant of the potential of a solid oxide fuel cell is the temperature. As you can see, even when you keep all else the constant, that is the reactants that are sent into the fuel cell is one and the same. The electrolyte and the electrodes are one and the same in these three systems. The only thing that is different is the temperature of operation of the solid oxide fuel cell. As you can see, when you increase the temperature, there is a significant increase in the potential. For example, if you have this particular current density, by operating the fuel cell instead of at 600 degrees centigrade to 800 degrees centigrade, there is a significant increase in potential. This increase in potential is because of decrease in mainly ohmic drop. For example, here, this particular overpotential or the ohmic overpotential is significantly different or significantly lesser at a higher temperature. So that is what is the ohmic potential is what decreases as you increase the temperature. So operating at a higher temperature is critical to the performance of a solid oxide fuel cell. In addition, there are other specific details that you should be aware of. One is that the entire solid structure has certain parts which are porous in nature, and there are certain other parts that are made up of dense solid structures. So here, the electrolyte is made up of a dense solid structure. The electrolyte allows only ions to pass through, but does not allow for the gases to mix. That is because on one side you have, let's say, hydrogen. On the other side, you may have oxygen or air. If there is a mixing of hydrogen and air, there is direct combustion, which you want to avoid in a fuel cell. So one of the reason for having a dense electrolyte is that it acts as a natural separator, separating the gases that are fed into an anode and the gases that are fed into a cathode. This porous structure has to serve different function. The essential function is that it has to provide for the three-phase boundary. That is, it should be there should be facile transport of the reactant gases and electrons, and it also has provisions for conduction of ions. So this porous structure has all the three transport processes operational within the structure, but here you have only ionic conduction. It doesn't allow for electronic conduction or for the transport of reactant gases. So because you have typically solids, it is important to understand the nature of the materials that go into making each of these components. What is been referred to as electrodes in all our past earlier lectures, in the SOFC community, the electrodes are referred to as interlayers. Mainly, they have two components. For example, they would have a ceramic component, but the ceramic component typically does not have sufficient amount of electronic conductivity. So the ceramics are mixed with metals like nickel, and these two together are called cermats, or the interlayers or the electrodes might be doped ceramics. So if they're oxides, it is important to note that these oxides might be facing a reducing atmosphere on one of the electrode, let's say at the cathode, or on the other electrode, you may have an oxidizing atmosphere. So if you have a metal, the metal should not get oxidized, or if you have an oxide, the oxide should not get reduced. So all these things are the material challenges that you have to consider when you are designing a solid oxide fuel cell. In addition, because the solid oxide fuel cell operates at a very high temperature, the coefficient of thermal expansion of these three components have to be compatible. Else, what would happen is that as you keep increasing the temperature of the fuel cell, there will be thermal stresses that are generated, which may lead to delamination of these components, or it may lead to cracking of the component. So there are a lot of material challenges that have to be solved before you can implement solid oxide fuel cell in a large scale. Because of the porous structure, the concentration inside the porous structure is different from the concentration in the bulk of the system. That is, so this essentially controls the concentration over potential. For example, the expression for concentration over potential at the anode depends upon the concentration of hydrogen at the surface divided by the concentration or the partial pressure of hydrogen at the bulk. So if this partial pressure is much less than this partial pressure, then the concentration over potential is significant. Likewise, you may also define a concentration over potential at the cathode, which is determined by the partial pressure of oxygen on the surface divided by the partial pressure of oxygen in the bulk of the system. So all these issues have been already elaborated in previous lectures when we dealt with concentration over potential. If you are unsure of the basis for these expression, you may refer to earlier lectures on transport in electrochemical system, which we have presented in the playlist on Introduction to Electrochemical Engineering. In addition, in an SOFC stack, what we mean by that, if you have one electrode electrolyte, that is anode cathode electrolyte, that is referred to as a cell. Bunch of cells put together forms an SOFC stack. In this SOFC stack, the anodes have to be connected with cathodes. The design of an SOFC stack will be dealt with in future lecture. But the main point we are trying to address here is that there are certain constraints that are associated with the materials that are used for connecting the cathode with the anode. First, they must be electronic conductors. They are like wires, essential for conducting electrons from between the two electrodes. And these are referred to as interconnects in the SOFC community. So typically, the SOFC is operated at high temperature. So metals that have high melting point, only these metals can be utilized as interconnects in an SOFC stack. So these metals which have high melting points or melting point greater than 2200 degrees centigrade are referred to as refractory metals. The typical refractory metals, which are tungsten, niobium, tantalum, molybdenum, and rhenium, are fairly expensive materials. So it is not very practical to use these materials. So one of the challenges in bringing down the costs of SOFC is to find an ideal material which has sufficient electronic conductivity so that they can be used as interconnects. And perovskite type of oxide ceramics are being explored for interconnects. It's important to understand that these interconnects connect a region of cathode, a region where there is reductive atmosphere on one side. On the other side, there is oxidative atmosphere. So the materials that are used as interconnects should not dramatically changed when they are exposed to reductive or oxidative atmospheres. So the typical inexpensive interconnects that are being considered are made up of perovskite type oxide ceramics. If the SOFC temperature is brought down even further, let's say from 800,000 degrees centigrade to less than 600 degrees centigrade, inexpensive steel can be utilized as an interconnect. This is one of an important reason for to bring down the temperature of SOFC. Steel is much less expensive compared to the refractory metals. Again, an important challenge whenever you are thinking about SOFC is compatible coefficient of thermal expansion of the three components. The anode, the electrolyte, and cathode should have compatible or comparable coefficient of thermal expansion so that the thermal stresses associated with changes in temperature is not significant. In addition, because the products of SOFC, let's say even H2O, are at very high temperature. So this waste heat, so to say, should not be just released into the atmosphere. This is not very productive. So there are a lot of approaches on how to utilize this waste heat in to do some other important function. One of the ways how you can utilize the waste heat is to supply this heat to a reformer. The reformer um, uh, undertakes an endothermic reaction. So the energy for a reformer can be supplied via the heat that is wasted otherwise in an SOFC. Or this waste heat can be utilized for running a Rankine cycle. If you're unsure of what a Rankine cycle is, you can look at certain lectures on thermodynamics. We also have that in another playlist on undergraduate thermodynamics, wherein Rankine cycle is elaborated. So overall, to have an SOFC, you not only have to have good electrical performance, that is, the chemical energy have to be have to result in sufficient generation of electrical power, that is sufficient voltage at sufficient current, which gives rise to sufficient power. In addition to this, in addition to electrical power, the waste heat should also be sufficiently utilized so that the overall energy conversion of chemical energy into electrical energy to overall uh, energy, usable energy, is high. Overall, fuel cells have been promising for more than 100 years. In fact, after the voltaic pile, fuel cell was developed even in late 1800s. Despite a lot of promise, large-scale utilization of fuel cell is yet to be realized. There are different reasons for this. Uh, there are two classes of fuel cells which we discussed, and there are different challenges associated with either classes of the fuel cell. Um, the PEM fuel cell um, have the challenge of expensive electrocatalyst and expensive um, electrolyte, let's say the Nafion membrane. The solid oxide fuel cells do not have expensive materials, but because SOFC operates at high temperatures, the issues of material degradation and stability at high temperature is a significant problem. So even though currently batteries are the dominant electrochemical energy storage devices that are used in electric vehicles, it is expected that to electrify larger vehicles like trucks or trains or even perhaps aeroplanes, fuel cells will be considered in addition to batteries. So, for smaller vehicles like scooters, motorbikes, and smaller cars, batteries are perhaps a better option as the size of the electric vehicle keeps increasing. Let's say from trucks to trains, fuel cell might be a better option. In addition to that, if you are thinking about stationary electrochemical energy conversion strategy. So fuel cell is typically an energy conversion device. So for a stationary system, a fuel cell might have a better advantage as compared to a battery. From the point of fundamentals, it is important to understand the polarization curve. As always, the underlying thermodynamics, electrochemical kinetics, and transport in electrochemical systems help you rationalize the polarization curve of a fuel cell. With that, we end these lectures on fuel cells. Thank you.